Good afternoon. I am a neurosurgeon. I'm talking to you about a brief history of time because I did a BS in physics and because I know this, I owe this university something that I'd like to give back. The best thing about the book is actually the title of the book, A Brief History of Time. In one sentence, they have three words that refer to time. It is time, history, and brief. We'll try to go through the book and make it understandable because I don't think that many people, me included, like this book. It's one of these most difficult books that you're going to get into CS. The book is divided into three parts. The first part is cosmology, Big Bang, and so on and so forth. The second part is relativity. The third part is quantum mechanics. I tried last year in 1 hour to cover all three of them. It was a failure. So this year we're only going to cover relativity. And I would ask you if you want to refrain from questions till the end of the lecture. I'd be very thankful to you. What is scientific theory? Scientific theory starts with an observation. I observe something, and then I'm going to have a theory about it, and then I will have a prediction, and I will conceive an experiment. And if the experiment is well done, it will lead to one of two possibilities. Either it will confirm my prediction, or it actually will prove that I was wrong in predicting this. Either way, I would have done one step forward in my scientific discovery. So the most important thing about a theory is that it has to be falsifiable. Falsifiable means that if I have a prediction, I should be able to construct an experiment that will prove it either right or wrong. I can sit here and tell you there are angels in the world. I cannot have any experiment to prove it or disprove it. A scientific theory is based on falsifiable experiments. So a scientific theory can never be proven correct. It can, however, be disproved. A scientific theory is correct until it is proven wrong. This is taken from a book in 1837. And you can see that this book is written in Greek. And this is a book actually from Aristotle, who lived in the 4th century before our era. So for 2,000 years, people used to follow Aristotle, not thinking whether he was right or wrong. So let us start first with the idea of time and the physics of Aristotle before we go further. Aristotle thought that the Earth was in the center of the solar system. So you have the Earth here in blue, and you have the planets going in circles around it, and the sun also would be going in circle around the Earth. This is what we call geocentrism. Aristotle thought that there were 4 elements: earth, air, fire, and water. So even at the time of the Greeks, even at the time of Democritus, they thought about something called atoms. Aristotle said atoms don't exist. We have 4 elements, and these are the 4 that are here. And more importantly for us, Aristotle thought that objects had a natural place, and they sought to return there, which meant that if you have smoke, the natural place of smoke is with the clouds, so the smoke goes up. If you have a piece of stone, the natural place of the stone is the earth, so the stone falls down. Okay. And also, Aristotle thought that motion needs force. So these are the tenets of the Aristotelian theory. Geocentrism, 4 elements, objects have a natural place, and motion needs force. So even at that time, Aristarchus of Samos said that the fixed stars and the sun remain unmoved, and the earth revolves around the sun. So people were not stupid. Even at that time, people were telling Aristotle, you are wrong. We see things that you cannot explain. But Aristotle was a teacher at AUB. Everybody, took what he said without discussing it. And we were there for 2,000 years with what Aristotle said. Now, Oscar Wilde, the great English writer, said, you are all in the gutter, but some of us are looking at the stars. And the first physics started by people not having TV, sitting and looking at the stars, and seeing how the stars moved and trying to make sense of this. And they found out that some of these planets, planet in Greek, okay, is a wanderer, because when people looked at the stars, they saw that they were fixed stars, and then in between the fixed stars, there were other small stars that would move with time. In winter, they will be here. In summer, they will be there. And they call these the planets, the wanderers. هدول تايهين بيمشوا. And they thought if the earth was in the middle and everything was rotating around them, okay, then we should not have, okay, a planet that goes and comes back and goes back, okay? They found out that some of these planets had what is called a retrograde motion, that a planet would be moving like this, will go back, and will move back in the other direction. And to explain this, they came out, they came out with this idea. They said, okay, this is the earth here in the middle, okay? And this is the planet. And the planet does not go directly around the earth in one circle. It goes actually in a circle around a circle. And this could explain this retrograde motion. And they were very happy. They decided, okay, now we have a system that can explain what we're seeing. And this is what they were seeing. Okay, the earth is in the middle and a planet that goes around what we call an epicycle. And you remember what I said, that first you have observation, and then you have to make a prediction, and then you see if you have an experiment or a theory, then you produce a theory, then you see if your theory holds or not. Even by doing this, they found out that some things were not working very well. So Ptolemy, in the second century of our era, decided that actually the earth was not in the middle of the circle. It was a little bit to the side. And that this place is called the equant. So now we had a planet that went around a circle based on another circle that was not based on Earth. And Ptolemy, really everything fit with him except for one thing. What did not fit was Mercury. And we're going to find out that Mercury causes trouble for people because Mercury never behaves in a way that is understandable for them. So now that Mercury could not fit into the scheme, who came along? Copernicus. I want to go back to this one just to show you that this was in the 2nd century, and here we are in 1500. So for 1,300 years, nothing happened. نحن هون من جمعة لجمعة we have a new app, and we have a new iOS. Here they stayed for 1,300 years thinking that Ptolemy was right, until Copernicus came around, and he said, no. We have the sun in the middle, okay, and everything goes around it. And this can explain the retrograde motion. Now, it is very important for you to know two things. First, that Copernicus was not a great mathematician. He put the sun in the middle and he put circles around it because it made sense for him aesthetically. It was beautiful. Okay? And then, like Dr. George Saliba proved, you had some Arabs that had done this work before. And if you look at Nasruddin al-Tusi, these are the exact same pictures that Copernicus took from him. So most probably, this idea of having the sun in the middle, the heliocentrism, came from an Arabic manuscript that Copernicus read, and he plagiarized it. Okay? And now we go to Tycho Brahe and Kepler. Dana is here. Where is Dana? Hi, Dana. Dana is in experimental physics. I'll tell you why. Because Tycho Brahe, no, ما بدي شيء منك بس عم بحكيك بس ما بدي شيء منك. Okay. Tycho Brahe was an astronomer who spent all his life in Denmark. Why in Denmark? Because there they had no cities. There was no light. He could look at the stars. And all his life, he was looking at stars and taking measurements and wrote them down. He never had any theory, did not do anything with them, nothing. He just spent his time looking at the stars and writing them down. And when he died, he left all his books to Kepler. So this is Tycho Brahe, okay, and this is Kepler. Tycho Brahe doing the measurements, and Kepler getting the books from him. And Kepler took these books, and instead of throwing them out, read them and looked at them, and he came out with the most important discovery. And he was a real mathematician, that actually the planets don't go around circles, but they go around an ellipse around the sun. So let's go back a little bit. Aristotle says the Earth is in the middle. Copernicus said the Earth is not really in the middle, it's a little bit off, but everything turns around it. Ptolemy says the sun is in the middle and there are circles around it. And Kepler, and this is the most important thing, goes ahead and says, okay, the orbit is an ellipse. Now, the next question is going to be, if this is so, why? And this is when we get to Newton. One of the biggest, is not the biggest scientific mind of humankind. So if you look at this, you can see that this is Copernicus, this is Tycho Brahe, this is Kepler, and now we go to Newton. And Newton asked why. He said, why aren't we going into circles? Why are we going into ellipses? And he proved that you go into ellipse because there is something that he called the universal law of gravitation. I'm not going to go through the details because maybe most of you are not interested in physics, but it's interesting to see that what Newton said is that any two particles attract each other. The Earth attracts me and I attract the Earth. The sun attracts the Earth and the Earth attracts the sun. And it is, okay, given by this equation. So the three laws of Newton were the law of the law of attraction, that acceleration is produced when force is exerted, and for every action there is an equal and opposite action. Okay, you have this in your notes. I think this is one of the most important slides if you want to understand how physics has evolved, and you have it in your notes. Aristotle, and 2,000 years later, Newton. Aristotle says that the Earth is in the center of the universe. Newton says that it is the sun. Aristotle says that motion needs force. And Newton says, no, change in motion needs force. So if I have an object that is moving, I don't need force to keep it moving. I just need force to make it either go right or left or to accelerate it. And Aristotle said that things went to their place of predilection, whereas Newton said that they were attracted because there was the law of attraction. And you can see that it took 1,000 years to go out of Aristotle into a system where now we can start thinking scientifically. And now we can start having experiments that we can disprove. And at that point in time, for those of you who need French, I read it for you. Nul n'atteindra la gloire de Newton, car il n'y avait qu'un monde à découvrir. Lagrange was a great mathematician. For those of you that don't understand French, he says, nobody will equal Newton because there was one word to discover and Newton discovered it. So at the time of Newton, we thought that we had finished, okay, from science. خلاص ختمنا العلم. How did we finish from science? Okay, first, there is determinism, okay? If I know all the prerequisites of something, I know where it's going to end. The word of Newton, this is very important because in a second we're going to change all that, believe me. He used to, at the time of Newton, we thought that there was a constant and common dimensions of space and time, which means that your centimeter is my centimeter, is your centimeter, is his centimeter. Your time is my time, is his time, is her time, okay? So time and space are common to all of us. And we are playing, we are having a play in a theater where we share time and space. And also very important is that we are in relative frames. And I'll tell you in a second what relative frames mean. يلا. روكب طولوا بالكم شوي. Okay, okay. So a little bit of physics. Okay, I am on a train, okay, that is going, okay, at a certain speed, okay? Let's say that my train is going at 40 kilometers per hour. If I am walking in the train at 10 kilometers per hour, okay, in 1 hour, I would have done 40 plus 10, 40 plus 10, which is 50 kilometers an hour, okay? We all understand this, okay? If I am in a train that is going at 50 kilometers an hour and I'm moving at 5, I'm going to be doing at 55 kilometers an hour, okay? So now we're going to go to the part of relativity and Einstein. And this is where it is counterintuitive. Counterintuitive, in a word, it means that it does not make sense, okay? It does not seem too likely to be true when assessed. It's different from what you would expect. So hold tight and let's try to understand what Einstein is saying. First, very early on, in 1676, people realized that light had a finite speed. Okay, it was a very, very, very quick speed, but it was a finite speed. And then, okay, they found out that it was 300,000 kilometers per second. 300,000 kilometers per second, it means that it can circle the Earth more than 7 times in 1 second. Now, we are down to 10% of what they found at the time. So they did really a very, very, very good job finding that. The most important discovery came with Mr. Maxwell, and you have his name in your handouts. What Maxwell did, he said he found out that electricity, magnetism, and light were all manifestations of the same phenomenon. But more importantly, he said that these electromagnetic disturbances travel at a fixed and never-changing speed, a speed that turns out to equal that of light. So what Maxwell said, he said, okay, guys, I don't understand it, but light in vacuum cannot go faster. Whether it is on a train, on a plane, or nothing, light always goes at the speed of light. And people did not understand that, and they tried to disprove it, and they could not disprove it. And there were many experiments trying to show that light actually had a speed that could vary in vacuum, and it did not happen. And what happened is that Einstein came along, and Einstein said, okay, instead of trying to disprove what Maxwell said, let us accept it and let us try to build a new theory beyond the theory of Newton. So, whereas Newton said that time and space were the same for all of us, Einstein, in his thinking, is going to actually change all that. And all that started because Einstein got convinced that Maxwell was right. The speed of light, okay, would not vary in vacuum. So when Einstein graduated as a physics major from the Polytechnique in Zurich, he wanted to be a university professor, Sam Adana. However, one of the professors he clashed with at the Polytechnique was able to close all the academic doors for Einstein. So instead of becoming a professor, he became a clerk in a Swiss patent office. يعني صار okay كشبنجي ببنك بالpatent bank. إنه يبعثوا له الأوراق وهو بيقول لهم إذا منيح أم لا. This is the great Einstein. From this position alone, and isolated from the academic world, Einstein burst into the world of physics and changed it forever. And he did so mostly in 1 year, in 1905, known as his year of miracles. Einstein wrote 4 articles in 1905. نحن بنقعد هون 10 سنين to write 1 article. He wrote 4 articles in 1905, and each one of these articles changed the face of physics. And he did it on his own, not with colleagues, not with the laboratory, nothing. قاعد هو بالpatent, signing for this and thinking about things. And I'm sure that this is when he told his professor this. Okay, and thanked him for that. So, these are the 4 articles. I'm not going to go through these, except just to tell you that he spoke about the photoelectric effect, the Brownian motion. And this is important because what is Brownian motion? People at the time did not know that the atom existed. So Einstein, sitting in his patent office, writes a paper, okay, that proves that atom exists. He wrote about special relativity, and we'll talk about it in a second. And he wrote this E equals mc squared. All these are in 1 year. All these are in 1905. So in 1905, he writes about quanta, and quantum mechanics is actually based on Einstein, even though he never believed in it and they had big fights about it. Quantum mechanics is based on Einstein, and Einstein got his Nobel Prize not for relativity. He got his Nobel Prize for his quantum work. I mean, for somebody who never believed in quantum mechanics, he got his Nobel Prize for quantum work. He wrote about atomic theory, special relativity. These three were in 1905. It took him 10 years to go from special to general. In the 10 minutes that I still have to talk to you, I'm going to tell you what special relativity is so we can clarify a few things, and then tell you what general relativity is.
You have half an hour.
Half an hour? Okay. بس ما بدنا نزهقهم. Okay. So the first thing that Einstein said is that the photon is a massless particle. And if you look at this, it really doesn't make sense because we always thought that particles had a mass. And if something was massless, it would be actually a wave. So if you say that it is a massless particle, it doesn't make sense. And that's where I start by telling you it is counterintuitive. You cannot understand it. But it does make sense if you're making calculations to the point that another Nobel Prize, William Bragg, used to say physicists use the wave theory on Mondays, Wednesdays, and Fridays, MWF, and the particle theory on TTS. So even the physicists had no clue what they were dealing with. They would teach that the light is a wave, and they would teach it half of the time, and the light is a particle, and we'll teach it the other half of the time. And for those of you who tell me that if you are a massless particle, then E equals mc squared equals 0, and light has some energy, the real equation is not this. The real equation is this, where this is the momentum. And even though the photon is massless, so m0 is 0, it has a momentum here, and that's why, a light carries energy. So in one of his articles, Einstein, in 1905, equates energy and matter and gives something called the energy mass, which tells you E equals mc squared. E equals mc squared is very important in our nuclear power plants, not to talk about the nuclear bomb. Okay? So this is one paper in 1905. So special relativity, this is the second paper we're going to talk about. It is based on two things. It is based on the first fact that the laws of physics are the same for all of us. Even though your time might not be my time, and your space might not be my space, but your law of physics are my laws of physics, and your laws of physics are mine. مش كل واحد منا فتح دكان على حسابه. And it is based, as I said, that the velocity of light in vacuum is the same for everybody. So, just to remind you, this is what, Newton said. I'm on a train going 40 kilometers per hour. I'm walking at 10 kilometers per hour. So in 1 hour, I would have done 40 plus 10, 50 kilometers. What Einstein said was different. He said, let's say that this is the train going at 100 miles per hour, okay? Sorry, at 50 miles per hour. And here I have two cops, okay? One sitting on the train and one sitting near the train. And they're at the same level. Here they don't look at the same level, but they are at the same level, okay? And they're both shooting with a bullet at 100 miles per hour, okay? The cop that is on the train, the bullet of this cop will hit the robber at 100 miles per hour. I mean, it makes sense. If you are in a train and you're playing, snooker on a train, your ball does not go quicker, okay? It goes, you cannot know if you're on a train or you're in your home playing snooker. So this, will hit this gentleman at 100 miles per hour. The cop that is actually not on the train, that is at the same level but not on the train, his bullet is going to hit the robber at 100 minus 50, okay? He will feel it less, okay? This is Newton. Newton will tell you this, okay? Now Einstein said, he goes from the premise that the speed of light does not change, and he tells you that if you are shooting him with a light beam, the two light beams will have the same energy. You see, this is the big difference. The big difference is that in Newtonian physics, when you're talking with bullets going at a speed that is a small speed, you have a relativity between the gentleman who's on the train and the gentleman who's standing on the side. If they are shooting with light, you cannot do this anymore. You cannot use the same okay, mathematics, the same relativity if you're dealing with light. So if you tell me this, we're going now to start talking about time. What is time? نحن قلنا a brief history of time. How do we define time? We can define time as measured by clock, but this will be like the chicken and the hen. What came first, time or the clock? Or easier to do, we can define time as something that goes in a regular cycle, okay? A regular cycle, يعني أنا بالموسيقى, they define time like this, and this is what time is going to be for us. So speed is distance divided by time, and time is the speed divided by the distance, okay? So if I have a photon here that goes down and up at a certain speed, for me to get time, I just have to divide the speed by the distance, okay? Now, let's say that my clock is actually moving. It's not a clock that is stationary. It's not, I'm sitting at the K with my clock. I am in the train and the train is moving. And the clock is moving. The photon will not go up and down like this anymore. It will go in zigzag. Going in zigzag from here, the distance will be much longer. I mean, this is a certain distance and this is a longer distance. So time will change in a moving clock. And to show you, this is from a video. And now look at the ping pong table that actually symbolizes the light, okay? This is your clock. And you think that it's going up and down like that. But actually, now we're replaying it, the ping pong ball does not go up and down, it goes in zigzag, and look what it's doing. This is the same exact video that we're replaying. So what you thought was up and down, regular, is actually zigzag. So in a moving clock, time will not be the same as time in a stationary clock. So if I am standing here and there is somebody in the train, I can tell them lengths are shorter and time is slower on the train. We just proved it now, okay? This is special relativity. But the problem is that the gentleman on the train can tell me, لا حبيبي, I am stationary and the whole world is turning around me. I mean, this is relativity. Who tells you that I am moving? It's not that the whole world is moving around me. So the gentleman on the train can say, no, lengths are shorter and time is slower on the ground, okay? People will start fighting. And this is one of the problems that Einstein had with his special relativity. Special relativity, okay, will give you different point of views, depending if you're in the car or standing by, and people cannot agree on the simultaneity of things. So something that I think, if I have two events, and I think they happened at the same time, if you are in a car, you might see one of them happen before the other, and you can tell me, they did not happen. And if you're in a car coming the other distance, you might see it differently. So people cannot agree, not only on time, but they also cannot agree on distance, and they cannot agree what is simultaneous. And this caused a big problem for Einstein. So he sat down and he started thinking about space-time. نحن قلنا for Newton عندنا space and time. Einstein said, حبيبي, no, we're going to now call it space-time. Space-time, okay, what is space-time? For those of you who like math, this is one dimension. ليش one dimension? Because one number gives me an indication. I can tell you on the ruler, it's on 3. I only need one number. This is called one dimension. If I have a plane, I need 2 numbers. So this is 2 dimensions. If I have a cube, I need 3 dimensions. What is a 4th dimension? It's very easy. I can tell you, I'm going to meet you on the 3rd floor of Nicely, we already have 3 dimensions, at 2 p.m. I added the dimension, now we have 4 dimensions, so time can be part of a 4-dimensional space-time, okay? Special relativity, this also you have it, and this is very important. Special relativity is restricted to the flat space-time. Flat does not mean 1 dimension or 2 dimension. Flat means very easily for those of you who have done math and for the rest, in a flat dimension, a triangle, the angles of a triangle, the sums of the angles of a triangle equate 360. So if you have, okay, a triangle, and the 180. Should I know? 180. It's okay. So this is what a flat dimension is. It does not mean that it is flat, but it means that, okay, the theorem of Pythagoras holds. So what Einstein said is something very easy. He said all objects in the universe are always traveling through space-time at one fixed speed, that of light. So he went from Maxwell saying that the speed of light was always the same in vacuum to saying we all travel in space-time, not in space, in space-time at the speed of light. Okay? We all travel. And now we are all now traveling in space-time at the speed of light. So this is space and this is time. Okay? For us, okay, because we go on a very small speed, we see that time is very important. So I can stand here, not move at all, and I'm actually moving in space-time on the time line. Okay? Even though I'm not moving in space, I'm moving in time. For light, it's just the opposite. Light goes so quickly that it actually moves in space and does not move in time. And that's why, for light, time does not exist. A photon, okay, does not feel time. A photon is, okay, eternal. It does not feel time. It does not decay. Why? Because it only goes around this axis. So we as a human being go on that axis. A photon goes on this axis. What we share with the photon is that we all go at this exact speed, which is the speed of light in time-space. I thought it's going to be counterintuitive, but you have to understand that this is the genius of Einstein, where he said we are all traveling at the same speed in space-time, which is the speed of light. So in 1905, okay, in the other paper, Einstein takes space and time, puts them together, and he has space-time. But even at the time of Newton, Newton had a problem with his theory of attraction, and he wrote it himself. He said that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, is to me so great an absurdity. So even Newton, who discovered gravity, said it was absurd. It was absurd because you cannot act at a distance. You cannot act in a way that was instantaneous. How can the sun instantaneously act on the earth? And he did not understand it. And it took Einstein 10 years to go from special relativity to general relativity to answer this question of Newton. What Einstein did is that he thought that there was no difference between an accelerated vantage point and a gravitational field. شو بيعني هيدا؟ هذا بيعني if I am, okay, in a train going at a speed that is not accelerated, I don't feel the motion. If I close my eyes, I don't know if the train is standing still or is moving. It is only when it accelerates or takes a turn because there's a change in the motion that I feel it. If I am in an elevator and the elevator is actually going up, I will feel it going up. But if I fall, I will feel the same thing. I cannot make the difference between acceleration and gravity. And he, by including gravity in general relativity, what he did is that he placed all the observational points of views on equal footing. يعني, special relativity, I can tell you your clock is slower, and you can tell me, no, your clock is slower. I can tell you your inch is smaller, you can tell me, no, your inch is smaller. By getting relativity included in general relativity, by getting gravity included, okay, Einstein said that, no, we can both agree how the clocks are working and what distances are. And he said that all the laws of physics must be valid. So to do this, now we went, you remember, we went from 3 space and 1 time to space-time, okay? And now Einstein goes further and he says, no, space-time is not flat. Space-time is curved. This is a flat space-time, and this is a curved space-time. And you can see that on a curved space-time, the angles of triangles are more than 180, okay? And what is also very important is that in general relativity, space-time is curved by the presence of matter. So this is flat space-time, and this is curved space-time. This here is important, okay, in special relativity. This is necessary for general relativity. So what Einstein discovered that in general relativity, there is no attraction. Attraction is geometry, okay? And he said, okay, matter, energy, deforms space-time, and by deforming space-time, it will force things to take a certain trajectory. So the shortest point on a flat space-time is a straight line. From A to B, this is a straight line. On the Earth, for those of you who look when you take a plane, what the curvature is, it's never a straight line. It's always a curve. So the shortest distance in a curved space-time is not the straight line. So objects move through space-time along the shortest possible path. And this is what you see here. Mass grips space by telling it how to curve. Space grips mass by telling it how to move, okay? So I have a sun here, it deforms the space. The space being deformed, the light of the star is deflected by this space. Just to prove that Einstein was right, Einstein thought that if you have a very distant star and it is going around, the light is going through around a star that is closer to you, the light is going to be deflected. You see, the light goes like this, is deflected and comes down like this. So for you, the star does not look here, it looks here, okay? And if you have one star here and one here, you will see the image of this as 4 stars. So people started looking at the sky to see if this was true or not. And they found something that is called actually the Einstein cross. And these are not 4 stars. These are 1 star behind this that we see as 4. And Einstein was proven right. So even at looking at the stars from Mercury that did not fit, so on and so forth, by looking at the stars, we know that Einstein was right. We're getting to the end of the talk, so it's very important just to recap special relativity, general relativity. Special relativity, the laws of physics are the same for all inertial coordinate systems. Inertial means that they're going at a constant speed without acceleration, and they're not having any turns. So what they are saying here, that the laws of physics are the same for all trains going at the same speed and not going right and left. General relativity said the laws of physics are the same in all systems. Whether you're accelerating or not, whether you're going right or wrong, right or left, they are the same. Special relativity does not include gravity. It took him 10 years to get gravity to fit in. So gravity is taken care of in general relativity. In special relativity, space-time is flat. In general relativity, it is curved. And as we said, in special relativity, we have equally valid perspective. فيك أنت تشرعني إنه my clock is going slower, and I can tell you your clock is going slower. Now, in general relativity, no. We know exactly which clock is going slower, and this is very important because every time you use the GPS is based on general relativity. If you were to do your GPS on Newton, you would lose 10 meters every day. So within a month, okay, Beirut would be in June. The only way that we can use GPS is by basing it on general relativity. So Einstein single-handedly, okay, by giving the general theory of relativity, had space, energy, time, and matter, all in one thing. And this is, okay, after being refused to teach in the university. منيح الله سترنا ما خلوه يعلم. So, as I told you, Einstein in 1921 was awarded the Nobel Prize for his quantum work. And I'm going to leave you here with a video, but before I put the video, I want to take a show of hands. Who of you has seen the movie Casablanca? واحد, اثنين, ثلاثة, أربعة, خمسة, ستة. In Casablanca, for those of you who did not see the movie Casablanca, there is a very important song called, okay, you must remember this. And I want to read you the lyrics of the song, how it starts, even though they don't sing it in the movie, because I'm going to show you the movie afterwards, okay? Not the movie, and this the excerpt. It goes, this day and age we're living in gives cause for apprehension, with speed and new invention, and things like fourth dimension. Yet we get a trifle weary with Mr. Einstein's theory. So you must get down to earth at times, relax, relieve the tension, and no matter what the progress or what they may yet be proved, the simple facts of life are such, they cannot be removed. You must remember this, and I will leave you with the movie, and I'll take... ما في صوت.
Play as time goes by.
Oh, I can't remember it myself. I'm a little rusty on it.
I'll hum it for you. Sing it, Sam.
Sam, I thought I told you never to play.
Please go out, rent the movie. It's a great movie. Thank you for your presence. Any questions?
It was great. It was really, really nice. بس I just wanted to ask حاطط في انت this one the velocity is distance over time and then حاطط time is
You are perfect.